Engineering and planning is the key to success for most heavy lift transportation and lifting projects. In this 60-minute video film you will see how and by means of what types of equipment 10 projects were executed. While we in no way suggest that the methods chosen were the only way in which the jobs could be carried out, each of the projects was awarded after a competitive tender and lessons can certainly be learned from the methods used. Please note, however, that while all the lifts were successfully completed, this video is purely an illustration of the events. Our first project looks at first sight like two giant hot dogs. In reality, these are two storage tanks for liquefied carbon dioxide, which were transported and erected in June 1989. Each tank weighed 260 tons, was 45 meters long and had a diameter of 6.6 meters. To lift them onto their concrete foundations, two 400 tons hydraulic cranes were positioned either side of the foundation. An existing pipe trench was bridged with some steel pontoons so that the tank could be maneuvered within reach of the cranes. The two cranes just had enough capacity to lift each tank from the trailers and set it on its concrete plinths. A detailed lifting plan was worked out so that each crane was positioned at a precise location. It was decided to belly sling the tanks with slings which were covered with canvas to protect the paint of the tank. Although lifting was carried out with two cranes working in tandem, overload of either of them was unlikely as the center of gravity of the load was located on the center line of the tank, equally spaced between each crane's lift point. As a result, lifting differences were unlikely to cause any overload. Hydraulic cranes were used on this project, as the columns could be erected on the foundations in just one afternoon. As a result, it was not necessary to mobilize and rig a single, larger, lattice-type mobile truck or crawler crane. Use of a jacking and skidding system incorporating hydraulic trailers was considered, but found to be uneconomical and therefore rejected. The transportation of this 220 tons refinery column with a diameter of 8 meters and a length of 38 meters was carried out on a set of Goldhover platform trailers. A Faun heavy-duty tractor pulled the transport combination, which consisted of an 8-axle-line Goldhover dolly equipped with a turntable at the front, while stability of the load was ensured by the use of a double-width 4-axle-line Goldhover with turntable at the rear of the column. To lift the column onto its 8-meter-high concrete tabletop foundation, a 600 tons DMAC TC3000 crane with 72 meters main boom and 150 tons of superlift counterweight was mobilized and rigged in a position close to the foundation. The TC3000 had 230 tons of lifting capacity at 60-meter radius, just enough to work with a 200 tons hydraulic tail crane and lift a giant column onto its foundation. To ensure the lift was vertical, each lifting lug at the top of the column was fitted with an 8-meter-long lifting beam. After the transport saddles had been secured against tipping, the column was lifted out of the saddles. The 200 tons tail crane was positioned halfway between tail point and main lifting lugs on one side of the vessel. Before a lift of this type is carried out, you should always check the actual size of the lifting lugs and make sure that they fit the shackle pins of the main lift crane as well as the tail crane. If they do not, you will not be the first person to find lifting lugs that have been designed without reference to the actual shackles used on the job. Shim plates are leveled and checked on the tabletop foundation before the start of the lift. Again, a detailed rigging plan was made to identify the correct position of the tail crane in relation to the main lift crane. Not only should the capacities of each crane be checked at various phases of the lift, but also boom clearance with the column as well as the lifting beam. Slowly the column reaches its vertical position. The load on the outriggers of each crane is spread by the use of steel pontoons. The tail crane is disconnected and slowly the TC3000 swings its load above the tabletop foundation. Do not forget to prepare a working platform around the tabletop, so that a working crew can safely position the column over its anchor bolts and secure it. Check the correct orientation and slowly lower the column's base ring without damaging the thread of the anchor bolts. Finally, the verticality of the column is checked from two directions and if needed adjusted before both cranes are released. In November 1991, this 320 tons reactor was transported to and erected in Dunkirk, France. When it arrived at a job site on self-propelled transporters, it had already traveled quite a distance by barge from Mannheim in Germany before being rolled off at Dunkirk. Here we can see the carousel mode of the self-propelled transporters. By means of a simple push-button control, the trailer operator can change the steering mode from normal driving to on-the-spot turning. In this mode, all wheels are positioned in a circle, and the self-propelled axles turn the transport combination on the spot, thus making the turn into the side road quite easy. The orientation of the load, tail end or front end, can also be changed quite easily if needed. Control is from a portable unit, which is carried by the operator walking behind the transporter. While preparing the spreader beam and slings, the ground level foundations were also prepared with shim plates and made ready to receive the reactor. In this project, a simple spreader beam was used. Support was given by additional slings and shackles which gave the correct length. At the end of each sling, a 3.5 meter long grommet with a 3 mm thick steel sliding plate was connected. This was fitted between lifting trunnion and grommet. A 300 tons hydraulic crane was connected to the tail point of the reactor, and the transporters were moved out of the way when the load was lifted from the transport saddles. To lift a 38 meter long and 320 tons heavy reactor, a DMAC TC3000 was rigged with 54 meters of main boom and 225 tons of superlift counterweight. With a rated lifting capacity of 340 tons, it was just sufficient to do the job. A 300 tons Liebherr LT 1300 was used as a tail crane and positioned on one side of the reactor. To clear the platform bracings at the top of the reactor, quite a complex maneuver was necessary. When the top of the reactor was clear, the leap pair lowered the base ring and the reactor reached its vertical position. The tail slings were released and the reactor maneuvered above its final foundation and set. Vertical alignment is usually done along the shell of the column. However, if the diameter is variable and the shell of the column cannot be used, a proper mark should be made at the top and bottom of the column in two different orientations. When the load is not particularly heavy and long slings are used, erection of a 36 tons column is possible without a spreader beam. On this particular project, a DMAC TC2000 was used as main lift crane and a 200 tons leap pair as tail crane. The job was relatively simple, as each crane had ample lifting capacity and was nowhere near its limits. Proper tailing and lifting lugs made the erection of this column a simple job. Each part of the lifting project is executed under the supervision of a rigging superintendent. The crane operator is instructed either by clear hand signals or by means of radio contact. Note that the operator has a very limited view of the job to be executed and needs clear instructions from the rigging superintendent during the entire lifting procedure. Wrong or unclear instructions could easily cause damage to the thread of the anchor bolts. Tighten the bolts, check vertical alignment in two directions and if necessary adjust the verticality with extra shim plates. Only after these checks have been completed should the main lift crane be released. As the sizes and weights of refinery columns get larger and larger, they often exceed the limits of a single lift crane, and we have to look for alternative methods. An example of this occurred in 1989 when two columns, weighing 480 tons and 512 tons, were transported and erected. The first column had a length of 76 meters, while the second one was even taller and measured 82 meters. The 480-ton column was transported on one set of two double-width 6-axle-line self-propelled transporter dollies with turntables. Maneuvering the column within reach of the two Demag TC3000 cranes with this sophisticated transport equipment was a relatively easy task. Despite extensive side compaction, extra steel plates were needed to make the road suitable for the self-propelled transporters. To facilitate the lifting of such a heavy and tall column, both lifting trunnions had to be carefully positioned at a specific orientation a few meters above the center of gravity. As both columns were to be placed close to each other, the lifting job was planned in such a way that after the erection of the first column, only one of the two Demag cranes needed to be relocated. The other could stay in its original position. To maneuver the column's lifting trunnions into position above the foundation and below the cranes, a temporary ramp and bridge was built. Once the front dolly had crossed and positioned the lifting trunnions within reach of each crane, the bridge was removed and the foundation cleared. Safely lifting such a heavy and tall column with two main lift cranes and one tail crane called for a variety of special precautions. Before lifting of the column started, it was necessary to make sure that both lifting trunnions were at the same elevation, and an engineer's level was used to check this. Any necessary adjustments were made with the main lift cranes. Once the lifting trunnions were horizontal, an inclinometer was installed on a swivel plate at the base ring of the column to monitor the horizontality of both lifting trunnions during the entire lifting procedure. By using this method, it was possible to precisely measure the height difference of the trunnions in relation to each other, and thus keep the difference to an absolute minimum. In this way, overloading of one or other of the main lift cranes was avoided. Controlling the lift is a rigging superintendent, who stayed in direct contact with the crane operators of the main lift crane and tail crane, and closely watched the angle on the inclinometer. One crane lifts at a fixed speed, while adjustments are made by increasing or decreasing the lift speed of the second crane. Slowly, the giant column rises between both crane booms, while the lifting trunnions are kept exactly in a horizontal plane. The tail crane, which in this project was a Demag CC2000 crawler crane, simply had to follow in with the base ring and keep it clear of the ground. The column was deliberately lifted to a height at which it could be swung in one continuous operation between the tops of both lift crane boom heads. This was the most critical part of the operation, as there was only a few inches of clearance between the column's shell and the top sheaves. Now the column had reached its vertical position and had to be lowered over the foundation bolts.
Vieren we, alle twee. Twee blokken. Ruud? Allebei vieren.
As the column was being lifted by two cranes, its orientation could not be changed while it was being lifted. It was therefore of the utmost importance that the orientation of the main lifting trunnions as well as the orientation of the tail lug were correct and regularly checked. The orientation at the base ring of the column should always be clearly marked to avoid any possible mistakes. Once vertical alignment had been checked, both lift cranes were quickly and easily released from the lifting trunnions. The second and even bigger column had a length of 82 meters and a weight of 512 tons. It was transported within reach of both lift cranes by means of a 12-axle-line single-width Scheuer platform trailer with turntable at the front and a double-width self-propelled Goldhover trailer with turntable at the rear of the column. Once again, the lifting trunnions were positioned just a few meters above the center of gravity, and a temporary bridge was again needed to position the column across the foundation within reach of both lift cranes. To erect this second, larger tower, one of the TC3000 cranes stayed in its original position, and only the second main lift crane had to be relocated. Both cranes, equipped with 54 meters main boom and 50-ton superlift counterweight, were connected to the main lifting trunnions and adjusted to the horizontal level of both trunnions, so that the inclinometer fitted to the base ring could be set to 0 degrees. In addition to the electronic inclinometer, a precise bubble spirit was also fitted in case of a power failure. All three cranes then lifted the column out of its transport saddles, and both sets of dollies were maneuvered out of the way. By specifying the correct position and type of lifting trunnions, these extremely large refinery columns were positioned using two main lift cranes and one tail crane. Both trunnions projected 650 mm outside the shell of the column, and this was just enough to swing the column in between the boom heads of both Demag TC3000 cranes. Obviously, The type and size of the lifting trunnions should correspond to the size of the crane boom heads. Originally it had been planned that a 400 tons Liebherr hydraulic crane would be used for tailing in, as the tail load was just over 90 tons. This was well within the Liebherr's capacity range, provided the column was placed correctly. However, unforeseen circumstances meant that at the time of the erection the Liebherr was not available and the CC 2000 crawler was used instead. This illustrates another point that is well worth remembering. Try to have a backup crane available to stand in or take over from the planned machine. We all know that this will happen from time to time. The lift has now reached the highest point, and the tail crane carefully swings the top of the column between both boom heads. 82 meters and 512 tons is now fully suspended by both TC 3000 cranes and can be lowered onto its foundation. It was October 1991 when our sixth project took place. 2 sets of Kamach self-propelled transporters were used to transport this 67 meters long column with a weight of 467 tons. With a diameter of 8.5 meters and a foundation that was in the corner formed by 2 adjacent buildings, it was a rather complex operation to get this giant into vertical position onto the foundation. In Western Europe, it is quite common practice to lift these columns with the help of 2 main lift cranes and a tail crane. Here, lifting criteria were, however, particularly tight. It was not a straight lift upwards, but a combination of lifting and slewing of both main lift cranes until the column had reached an elevation at which it could be swung over the adjacent steel construction. Available lifting height was also critical. Therefore, the main crane hook was replaced by a lifting grommet which would rotate around the pin in the main lift block during erection. Both transport saddles were lashed on the trailer to avoid tipping, and the steel stripes were cut loose. Yes, next time he will wear safety goggles. As usual, the inclinometer at the base ring is installed to monitor the level of both lifting trunnions during the entire lifting operation. Slowly the column is lifted from the trailers so that the self-propelled transporters with saddles can be rolled out of the way. The advantage of the self-propelled transporters is that it can drive sideways as well as forwards. All maneuvering is controlled by a portable remote control unit. Lifting of the column continued until it had reached the elevation of the adjacent building. While the transporters are driven away, the load on the main lift cranes is increasing. An additional counterweight has to be installed on the superlift tray. With the top of the column just above the structure of the nearby building, both cranes slowly lift and swing until both lifting trunnions are exactly above the foundation. At the same time, a close watch is kept on the inclinometer. The DMAC CC 2400 tail crane is slowly following and keeps the base ring off the ground. Slewing of both main lift cranes is not required anymore, and it is now just a straight lift upwards. The same procedure repeats itself. Lift the column high enough and keep both lifting trunnions at a horizontal level. Then swing the top of the column in between both boom heads. Slight luffing of both main booms can be done to increase the clearance. To facilitate lowering over the foundation bolts, cone pipes were placed over 3 bolts to act as guides. Alignment is checked, bolts are tightened and cranes released. Another column safely placed onto its foundation. Two columns were placed for this job. The first was this 106 meters long, 470 ton column, which was placed by 2 DMAC TC 3000 cranes. To erect the second, even bigger column, both cranes were relocated and rigged with 54 meters of main boom. This time, due to its enormous length of 112 meters and a weight of 634 tons, it was decided to erect the column in 2 pieces. Both lifting blocks were connected with grommets to the main lifting trunnions, which were positioned 44 meters above the base ring of the column. The weight of this bottom section was 513 tons, with a length of 88 meters. Near the tail point at the base ring, an inclinometer was fitted, so that the horizontal position of both lifting trunnions could be monitored during the erection procedure. The locations of the transport saddles were again painted and final preparations were made to start the lift. With a lifting capacity of 340 tons per crane at 11.5 meter radius, this was just within 75% of the rated lifting capacity. The column was positioned with its main lifting trunnion exactly above the foundation, so that both cranes were simply required to pull her straight up. The TC 2000 tail crane was placed to one side of the column and slowly followed with the base ring just keeping it off the ground. In order to increase the maximum lifting height of each crane, the main lifting hooks were removed and the grommet directly connected around the shaft in the main crane block. Slowly, the column was lowered down by the tail crane, while every movement was carefully monitored to ensure it didn't touch either crane boom head. The inclinometer was removed as well as the tail crane shackles. Suspended by two 500-ton DMAC cranes, the bottom section was slowly and precisely lowered down over the foundation bolts. Special guides were screwed on top of a number of bolts to help the base ring to be guided along the thread of the foundation bolts and onto the concrete foundation. Both lifting tackles were released and the vertical alignment of the bottom section was checked and adjusted within allowable tolerances. The foundation bolts were then tightened. Preparations were next made for an even more challenging task, the lifting of the 121-ton top section on top of the 88-meter high bottom section. Again, both cranes were relocated to a new position and rigged with 78 meters of main boom and 42 meters of fly jib. With a lifting capacity of 85 tons at 25-meter radius, each crane could reach to an incredible height of over 120 meters. Main boom and jib were assembled and the lifting block reefed to meet the required 85-ton lifting capacity. Slowly, the boom and jib were raised into vertical position with the main block above the lifting trunnion. Thin steel sheets were fitted to each trunnion and greased to facilitate the turning of the lifting slings around the trunnion. Both cranes were rigged with an outrigger base of 14.5 meters and fitted with 100 tons of superlift counterweight. Slender columns of this length are obviously affected by wind, as can be seen from the 106-meter high tower, which was erected a few days earlier. Again, the inclinometer was fitted at the base ring in order to monitor possible overloading of any of the cranes during the lifting procedure. The tail crane slings were prepared and connected to the tail lug and the inclinometer calibrated and checked. Finally, on the 6th of August 1991, the top section was lifted from the self-propelled Kamach transporter. The Kamach was driven away from under the load, and a few moments later the top section was moved from the horizontal to vertical position. With the load suspended by both fly jibs at a height of over 120 meters, a canvas tent was attached to protect welding work that would be performed at a height of 88 meters when both sections were connected to each other. Gradually, the 23-meter long top section reached its required height, and now the most difficult part of the operation started: slewing both cranes with its load above the 88-meter high bottom section. The inclinometer is still connected to the bottom ring of the load, so that the levelness of each lifting trunnion can be monitored. The rigging superintendent had taken up position on the platform at the top of the bottom section and instructed both crane operators by means of walkie-talkies. Special flanges were fitted to facilitate the connection of this 121 tons top section onto the bottom section. A well-engineered and complex rigging project came to an end successfully. In some cases, the lifting of large columns can be carried out more economically by using a mass gantry system. Usually, this is only the case when the weight of a column to be lifted exceeds the lifting capacity of cranes which are available. One example where lifting of a column was carried out using a mass gantry system is shown here. It was the lifting of 12 columns for a gas processing plant in East Malaysia. The contractor had decided to use a guyless mass gantry system with a strand jack placed on top of a header beam of the gantry. A hardwood timber matted area was prepared on which the 225 tons column was maneuvered under the lifting slings of the mass gantry system. The bottom end of the gantry system consists of a large steel frame on which concrete counterweight is placed to ensure the stability of the gantry system. In this way, the use of guy lines was avoided. A steel tail frame with a jacking system, guided on a rail track, is used to keep the column off the ground at the base ring. Lifting power is developed by a remote-controlled strand jack, which is placed on top of the lifting gantry and controlled from a container at the bottom of the masts.
see on the TV camera there in here.
Video cameras installed at the top show the operator in the container the progress of the lifting operation. A few years later, the same contractor decided to use a large crane for the erection of heavy loads instead of a mask entry system. The cranes used were a DMAC CC 4800, an American hoist 9310 and a Manitou 4600, which had to be mobilized to East Malaysia. Getting these huge cranes to a remote site isn't always easy. The crane was brought in on a flat-top heavy lift barge and rolled off at a jetty approximately 8 kilometers north of the job site. With a width of 12.5 meters over the crawler tracks, the car body could just be maneuvered in between the customs house and a tree at the other side. The yellow support structures in between the crawler tracks are placed on timber mats and jack the crane up to a height so that both tracks can be removed for transport over the road to the job site. An 8-axle-line Cometto platform trailer has loaded the 150 tons car body without tracks and transported it to the job site. Erection of various columns on the job site had already been started using a Manitou 4600 crawler crane. With a weight of only 80 tons, the column could be erected with a telescopic P&H crane used as a tail crane. This story repeats itself over and over again. Connect the main lift crane to the top lifting trunnions and the tail crane to the tail lug. Lift the column out of the transport saddles and gradually move her from the horizontal into the vertical. Make sure that both crane lifting tackles stay vertical during the entire lifting procedure. Then release the tail crane and slew the column above foundation and place her over the foundation bolts. At the same time, the CC 4800 is transported to the job site, followed by both tracks on a separate platform trailer. The first heavy columns arrive on the job site and are maneuvered under the reach of the DMAC CC 4800 and American hoist tail crane. The DMAC was rigged with 90 meters of main boom and superlift counterweight bogie in order to limit the maximum ground load to less than 10 tons per square meter. It was placed in a central position at the plant, from where it could erect almost all columns. The first column was a unit of only 100 tons, which was lifted into the vertical position and then slewed towards the foundation at a radius of 42 meters. The crane was placed on a base of crane mats with 4 hydraulic activated outriggers in between the crawler tracks to absorb approximately 30% of the load of the total crane. The superlift counterweight was placed on a special bogie connected to the back of the crane and hydraulically propelled to follow the slewing of the upper car body. With this attachment, the crane weight is better distributed over both crawler tracks and outriggers. A disadvantage is that the turning radius of crane and superlift bogie are increased to 26 meters and take up quite a bit of space on the job site. The CC 4800 can also work with a superlift counterweight tray, which greatly reduces the large turning radius. With its enormous lifting capacity at large radius, almost all columns and reactors could be placed from this centrally selected location on the job site in a very short period of time. In order to reduce on-site construction work as much as possible, quite a few contractors decide to install columns and other plant equipment in as large sections as possible. Here, a completely dressed out column is being transported from the port of Kalundborg in Denmark to the job site at the Kalundborg refinery, approximately 4 kilometers away from the port. The transport had to be performed after midnight in order to minimize traffic obstruction. To erect this 45-meter long column with a weight of 297 tons, a DMAC CC 4800 crawler crane with 90 meters of main boom and a DMAC TC 1200 truck crane were used. The column was lifted out of the transport saddles and gradually moved into the vertical position. It had to be placed on a 10 meters high tabletop foundation, but could only reach that position by being lifted over some adjacent reactors which were erected a few weeks earlier. You may have noticed that personnel on the job are dressed as they should be and are wearing protective overalls, hard hats, safety belts, safety boots and safety goggles. In the earlier projects shown in this video, site requirements and conditions were not applied so strictly. With today's stricter safety requirements and the frequent need to perform under ISO 9000 quality standards, most contractors now adhere strictly to site safety rules. When the column had reached its vertical position, the crane moves a few meters forward on the method path. Then the load was slewed over the existing reactors so that the superlift tray with 480 tons of counterweight at the back of the crane could be connected. With this additional counterweight, the crane had an increased working radius and could reach out to 40 meters, at which point equilibrium was reached between the load and the superlift ballast. Again, the crane moves a few meters forward to get the column exactly above its 10-meter high tabletop foundation. It is a spectacular sight to see how just a few men can turn this giant column and carefully place her on the foundations. That same night, a complete pipe rack module is transported to the job site via the 4 km long transport route, which was prepared long before the ship's arrival. Although detailed rigging studies had been prepared long before arrival of these large loads, final adjustments were made in the on-site office with the assistance of an AutoCAD drawing program. Progress reports and planning schedules are all prepared with the help of modern computers on site. Final rigging plans were discussed between the rigging superintendent and crane operator. To ensure that the module stayed in horizontal position while being lifted on a single hook, the location of the center of gravity was calculated and verified by weighing prior to shipment. On site, special link plates were installed to mark the exact location of the center of gravity. All engineering work proved to be correct. When the module was lifted from the trailer, it stayed in horizontal position. Once again, the superlift counterweight was used and the crane boomed out until the load was above its final foundation. Hi, I'm Richard Krabbendam. I hope you enjoyed our video presentation and look forward in showing you other interesting projects in the very near future. In case you like extra copies of this tape, please contact International Cranes, the magazine for crane users and buyers.